Hi there and welcome to this video for Senior Physics on Electromagnetism and Electricity. In this video we're going to add to what we learnt in our last video on transformers, and we're going to be using the PhET simulation. So basically, in order to load up the PhET simulation, you need to go to this website here, and basically it's a free website so you can download it. I've also put a copy of the link in the post so that you can actually click on and play with it in your own time. But basically what we're going to do is use this simulation to basically show you how transformers work. So what we're going to do is just open up the simulation, and what you will get, you're looking for the transformers section when you download that simulation. Now remember, just like I said with the generator, we've got the bar magnet, pickup coil, electromagnet and generator, all of which we've looked throughout this electromagnetism course. Okay, so what we basically get, if I open up the screen here, basically what we get is a power source which is generated through a single current, through a single coil, and then we have another coil over here which is basically linked to a light bulb. Now at the moment we've got AC current running through the power source. Now if I come over to the far side, you can see that I can alternate between DC, where I've got a current, just a direct current which is generated, or I can use my AC. Now before we go any further, let's just recap on what a transformer does. What a transformer does is mutually induce a current into a secondary coil. Now generally you would use an iron core to link the two coils together. In this case we don't have the core, but we can move our coils close to each other. Okay, so basically let's start the simulation. So what I'm going to do is we're going to start off with just DC. Okay, so I've got it sitting at 0 volts, and you can see the electrons are not moving, and as a result we've got no field which has been generated. So if I push this coil close to my secondary coil, nothing happens. And remember, we're looking for the light bulb to open up. Okay, so let's get the current beginning to move. Let's put it on 5 volts. Okay, now you can see here that what we've got is a magnetic field which has been generated, and you can see this by the field lines being pushed. Now you can see that those field lines are continuous all the way through the area of the secondary coil. Now even if I move the magnet close, you'll see there's no effect on the actual coil as I leave it stationary. But if I start moving it, can you see here that you've got some slight push or orientation on the electrons as it's pushing or going closer, and you can see the field lines moving. Well, the field lines are moving, and as a result, that's with time, that's a change in flux. Change in flux produces an EMF. That EMF, as we know, generates a current or a voltage. Okay, let's push it up to 10 volts. You can see at a stationary position there is no change in flux, so nothing happens up here with the light bulb. I can now move it in and out and change the flux. The faster I move it, you can see the more EMF which is going to be generated. Okay, so what we can then do is we see that DC doesn't work particularly well because we're getting no change in flux. But what we can do is now add AC. So I'm going to move my coil right over here, and I'm going to flick over and put on AC. Now you can see with AC, what is actually happening is the electrons are going one direction, then they go in the other direction. Positive, negative. And you can see what's happening to the field lines. They are altering. Now at the moment, the distance away is too great for there to be any effect. But look what happens when I start moving it closer to the first coil. And I can move it right over that first coil. And what I suddenly see is that my electrons in my secondary coil are also moving. And you will notice that that is due to the change in flux which is generated. Now if I decrease my loop area slightly and try and get them the same, just pull it down here, we can see that we've got a movement in the electrons similar to the change in flux which is generated, and you can see the light bulb going on. Now basically what I can then do is then add coils to this secondary loop. At the moment it's not working particularly well, but if I add another coil to the loop, let's see what happens to the light. Let's just go back actually and look at one, okay, and we'll put it in here and we'll just try and remember what the lines are like for the light bulb. You can see they're being generated, but they're not particularly great. But let's see what happens if I put a second coil in. Now what you'll notice is that the lines have actually increased. What I've done here is actually stepped up the energy which has been produced from the AC current of my primary coil and produced a secondary coil producing more voltage. Let's put another loop in and we should see it go up yet again. And you can see there that the light bulb has now gone up. Okay, so what's happened is the primary coil has produced an EMF. This has been passed over, or actually produced a change in flux. That change in flux has been passed over to the secondary coil. When there was the same number of coils, what we found was the amount of voltage was the same in both primary and secondary coil. Add another coil to the secondary, and what that means is I've increased from 1 to 2, so I've doubled the amount of voltage. Add another coil going from 1 to 3, and I've tripled the amount of energy which is generated. Now I can basically look at this in a little bit more detail by actually changing the amount of change in flux which is occurring, and this can be done by actually increasing the frequency of the AC which is generated. Now what I'm going to be getting is a lot of movement and a lot of change in flux. So let's go back and put one loop in, and I'm going to move my flux so it's basically getting closer, and look at the size of the lines which are generated on the light bulb just with one coil. Now let's put a secondary coil in, and let's put a third coil in, and you can see I'm getting massive introduction between, or massive amounts of voltage being generated outside compared to inside. Now I can also have a look at this with respect to changing on a voltmeter. Okay, so let's start off with one coil. Place it close here, and you can see the voltmeter is basically interacting. Remember, the wires are not linked. This is solely due, this voltmeter needle is moving solely due to the change in flux. Okay, but remember, in a transformer I want to increase the amount of voltage which is produced or decrease it. So increase the number of coils and increase the number of coils again, and we can see that it's being increased up. Okay, so that basically covers the idea of stepping up the voltage. So let's go back to our original situation. I'm going to keep the AC as it is because we've noticed that by changing the frequency I increase the amount of change in flux which is occurring. Remember, that's going to produce my EMF. So what I'm going to do now is I'm going to actually add more coils to my loop and do a step down voltage. Okay, so I'm going to add 4 coils to my loop, and I'm going to add 3 coils to my my secondary coil. So 4 coils to the primary, 3 coils to the secondary. Now you'll notice we can't go any higher. The simulation doesn't allow us to go higher. But basically what we're going to now do is basically decrease the number of coils in the secondary. And what we should find is that we're going to start off, I'm going to bring this nice and close. Okay, what we've got is this lovely light bulb flashing away. It's really, really good. Now, what I'm going to now do is step down the voltage. Now, I step down the voltage by decreasing the number of loops in the secondary coil. So I need less loops in the secondary coil than I've got in the primary coil. So let's step it down, and we should see the lines on the light bulb decrease. There you go. You can see them dropping down. Okay, and I'll drop them down again. and you can see it decreases. So this is a step down transformer. Why? Because I've got less voltage coming out than what I started with. So how is this useful? Well, if you can imagine, if I've got an appliance, remember I've got 240 volts coming out of the mains, and I've got a appliance that works on 6 volts, I can decrease the voltage using a resistor, obviously, or I could use a transformer. Likewise, if I've got an appliance that wants to work on higher than 240, I can then step it up. And in this case, I'd use a transformer, add more coils on the secondary coil than the primary coil, and the result is my voltage output will be a lot greater. Okay, so basically that shows exactly what happens when I'm using these change in flux to generate an EMF, an electromotive force, which causes electrons to basically move through a circuit, which will allow us to produce a voltage. Remember, the wires are not linked. All that happens with the transformers is that change in electric field is passed through an iron core. Well, I hope you found that useful. Hopefully you'll be able to go away and apply some of what we've learned in this simulation and what you've learned in the previous transformer video, and you can apply it to this simulation and play, well, what happens if I do this? What happens if I do that? Okay, so that basically means that we've now completed everything on electromagnetism. So thank you for watching. I hope you found it useful. Please do rate the site if you found it useful. I do like to hear your comments, what I can do to actually improve the site or improve upon any of the videos we've got. And look out for more coming up in this post. We'll be looking at electronics and seeing how we can convert AC to DC using capacitors and diodes. So I hope you'll join me for those videos, and I look forward to seeing you again. Thank you for watching.